All right, how's everybody doing? Professor Bryant back again with another problem directly from the review packet, also about light photons, particularly as it pertains to the photoelectric effect and threshold frequency, work function, all language that relates us to the exact same thing. So if we take a look at question 3 on page 183, we will see that the question asks us, what is the maximum wavelength, very important term there, of radiation, electromagnetic, which in this case is light, remember, that can cause electrons to be ejected. We remember this from our conversation of threshold frequency and work function from the surface of lithium metal in a photoelectric cell. The ionization energy, which we haven't directly discussed, but effectively this is the energy it takes to remove an electron. This is just stated differently because the units are different, and it tells us the ionization energy is 513.3 kilojoules per mole. Now, approaching this question, given that we understand that it takes a certain amount of energy to remove an electron, a lot of people will make the mistake and utilize this equation here. However, this is not the equation that we need, because this is for determining the kinetic energy of the electron once it has been ejected, based upon the difference between the energy of the photon and the threshold frequency. Another very important thing that we must get from the problem is that the maximum wavelength means the minimum energy, okay? So the minimum energy is the energy that is equal to the ionization energy, but not in the units of kilojoules per mole. We need to turn this energy into kilojoules, very similarly as we saw in a previous example. So we would do that by converting 513.3 kilojoules per 1 mole of lithium. We will convert that by dividing by Avogadro's number. And what that does for us is that eliminates the term of moles of lithium. It also will give us a value in joules, and we can convert that if we would like to. It gives us a value in kilojoules, and we can convert that from kilojoules to joules by using dimensional analysis. We will see that this value gives us 8.53 times 10 to the negative 19. Joules. Essentially, this is per atom or per lithium, right? Per electron that we are going to eject. We do not have to write this here, but we must understand that. That's the disconnect that a lot of students are going to make in this problem. So now that we have a value in joules, we can find the maximum wavelength, because the maximum wavelength will be the minimum energy, aka this value. And what does that look like? Well, if we know that 8.53 times 10 to the negative 19 joules is equal to hc over lambda. Again, where do we get this? This is E. We know this equation because this equation is also equal to h nu. But since we have been asked about wavelength, we are not concerned with frequency. So to solve for wavelength, we would multiply both sides by lambda and divide both sides by the energy, and we end up with hc over E. And in this case, 6.63 times 10 to the negative 34 joule seconds multiplied by speed of light, 2.99 times 10 to the 8 meters per second to the negative 1, all over the value we calculated previously, which is the energy per electron or per atom that we will eject an electron from in joules, and we find ourselves left with a unit of meters. The reason for that, and hopefully we are familiar, that joules is kilogram meter squared second to the negative 2 times seconds times meter times seconds to the negative 1. And this is all over kilogram meter squared second to the negative 2. And if we look at all of this, we will cancel out seconds to the negative 2. We'll cancel out these seconds. We'll cancel out meters squared. We'll cancel out kilograms. And we find ourselves left with the unit of interest, meters. Now, this value is 8.53 E negative 19. Looks like 2.32 e to the negative 7. Which is also 232 nanometers, which is in the UV. And that makes sense, right? UV light is powerful enough to remove electrons from many different materials. So again, a quick recap. We must recognize from the problem that we are trying to figure out the maximum wavelength or the minimum energy that can cause electrons to be ejected. We have been given that energy in kilojoules per mole, which means we will likely have to use Avogadro's number at some point, but we can relate that energy kilojoules per mole directly to the wavelength of the photon using the energy equation of E equals hc over lambda, but we must do this first step of conversion first. This is important. Once we find this value in joules, we can utilize E equals hc over lambda to determine the wavelength of a photon that can eject an electron from the surface of lithium metal. Again, as always, if you have any questions, be sure to drop me a line via email.